performance of the actual channel. And they overlooked a very important factor. What they didn't realize, oh, okay, I'm very sorry. I skipped a view graph. I got it in 3 a.m. this morning, 3:30 a.m., so I'm not quite up to where I should be. Anyway, let me talk about chromatic dispersion, because in order to understand this other thing that they didn't realize, you have to understand this too. The third contribution is chromatic dispersion. I think everyone might be familiar with that. That's how different wavelengths propagate at, or different colors propagate at different speeds as well, and they refract, they spread out because of that. But chromatic dispersion, even if you had a spectrum, the same a spectrum within one mode, so you have a number of wavelengths in one mode, those wavelengths will see different refractive indices, and they spread out as well. So chromatic dispersion is the third. Now we get to the fourth, which people didn't realize is what happens is it turns out that VCSELs don't emit the same spectrum into all the different modes. The longer wavelengths go directly into the lower order modes. They come out more perpendicular of the laser, from the laser, whereas short wavelengths come out at larger angles. And what I show on the bottom here are 4 different images of where the light, the different wavelengths are in the optical fiber. And you can see that lambda 2, which is going straight through, you can actually see it in the image that it's located kind of towards the center. And the shorter wavelength you can see is kind of in a donut. So because you have different wavelengths now in different modes, now you have a combination of modal and chromatic dispersion. So if you have if you do make a perfect fiber, because the refractive index of short wavelengths is different than long wavelengths, you'll then get a modal chromatic interaction. And this is the biggest problem when you start hooking up a fiber to a VCSEL. You're going to be dealing with this kind of a problem. But it turns out it can be compensated for. So if you get a fiber that has an alpha 1 where you have lower refractive index on the outer region of the fiber, you could actually bring those back together. And we have a fiber called signature core that is a refractive index that's just selected in order to bring those back into equilibrium. There's a huge difference in performance. Again, as I mentioned, these 2 fibers, same manufacturer, same cable, same bandwidth at 850. But if you hook them up to a VCSEL, a Ethernet compliant VCSEL, you'll see completely different performance. And what I show here, don't worry too much about the vertical scale. This is just telling you errors, the error rate. If you go up, that's bad, you're getting more errors in your channel. You go down, it's good, you're getting less errors. And what it shows is 5 orders of magnitude difference between these 2 fibers when you hook it up to a VCSEL. Even though the modal dispersion is the same, the chromatic dispersion is the same, the modal chromatic interaction, that because of the way the light is being launched into these fibers, one fiber will work and one won't. It turns out that 25% of the fibers that you have will not support the maximum reaches of the Ethernet, 300 meters. So OM3 will actually, if you have a good OM3, one that has an alpha 1, you'll actually go much further than 300 meters, whereas the one that has an alpha 2, you'll only go about 250 meters. And that wasn't a problem in the past because no one really went those kind of distances. But as you go to higher data rates, it's extremely important because you're now pushing them. So that gets us down to the different fiber types. OM3 and OM4 fiber, these are legacy fibers. They were standardized essentially 16 years ago, and half of them will have the alpha 1, the other half will have alpha 2. So half of them work well, half of them won't. And there's no way for you to tell which one is which. So what the transceiver manufacturers are doing to solve the problem is we're providing them with these alpha 2 fibers, worst case fibers, and they're now making transceivers so to meet the minimum reaches that are specified in the standards. So that's the fix for that. Signature core fiber is just an alpha 1 fiber, so we provide a spec to our fiber suppliers that specify a very precise refractive index profile in order to compensate for the effect of the monochromatic dispersion in order to bring all those modes back into equilibrium. Because of this problem was so big that we actually in TIA went to the standards body, and OM5 is essentially a commercial version of Panduit's signature core fiber. It's basically an A1 type fiber. So we chaired the development of that standard, and the only thing about OM5 is it's basically an OM4 with kind of an alpha 1. They don't have exactly an alpha 1 because Panduit owns the intellectual property on that. And fiber manufacturers, even though we said we'd give it to you, it's their business. They didn't want to rely on anyone else's patents to make their product. So it's not exactly an alpha 1, but it looks more like a signature core. And this is what the bandwidth actually looks like. So again, I'm using those two fibers, which are the two extremes of OM4. The OM5 is that black dashed line. You can see it's actually an alpha 2 type fiber, but what they've done is they made it work better at longer wavelengths, and it's reduced a monochromatic interaction. The other difference is that the OM5 is specified at a longer wavelength of 953 nanometers, where OM3, OM4, and even signature core is not specified at a longer wavelength. So although we do meet a certain value. So OM5 is an OM4 that's specifically designed for multiple wavelengths. That's when you would need it. But multiple wavelengths also have a problem, which I'll get into in a minute. The other thing that you probably need to know is that there's a lot of misinformation going on. People may be telling you that the OM5 is a next generation fiber. As a matter of fact, at the TIA, we didn't want to call it OM5. And we had a lot of, even Corning didn't want to call it OM5. So we didn't want to give the customer the wrong impression that this is truly the next generation multimode fiber, because it's really not. We wanted to call it OM4W for wideband OM4, but there were other companies out there that want to sell the next generation fiber, so they called it OM5 and they won. But there's disinformation associated with that. What they're saying is that OM5 has lower chromatic dispersion than OM4, and that's the reason it works better. And that's completely untrue. That's false. It turns out that what happened was during the standardization of OM5, Corning came to the standards body. This is actually their slide, the image in the middle. And they said that when we specified OM3 and OM4, we made a mistake. The chromatic dispersion in those classes are actually much lower than what we specified. So we did a round robin to verify that. And sure enough, all multimode fiber glass has a much lower chromatic dispersion than what we originally specified.